Welcome to part 4 of our Introduction to HPC video workshop. At this point, you should have already completed part 1 of the tutorial along with watching the video on the acceptable use policy. You should also have completed part 2 of the tutorial on storage and file transfer, along with the video on navigating the different types of HPC storage. Finally, you should have completed part 3 of the tutorial on running jobs. In this final episode of the Basic HPC Workshop, we will talk about parallel jobs. There are a lot of terms that are used while describing parallel computing, so first we'll spend some time defining these terms. We'll define jobs, tasks, and threads. We'll define hardware terms like nodes, processors, and cores, and I'll show you how to find hardware specs for the different nodes on the cluster. Then we'll define software terms, and these are the terms used when writing or running parallel programs. This will include additional discussion on tasks and threads, and it will include the definition of serial jobs, shared memory jobs, and distributed memory jobs. Then, finally, we will discuss and run parallel jobs. In the tutorial on running applications, we went over a basic batch script to submit a job. One of the required elements of the script was b sub minus n, where we specified the number of cores. Sometimes it's more accurate to say that n is for tasks rather than cores. A job is a set of tasks, and you usually ask for 1 core per task. Our sample R script did a single task. It created a PDF file with some temperatures in it. This was a very small example, and if that's all you ever needed to do, you probably wouldn't be watching an HPC tutorial. You probably want to submit a job that either does a giant task or a giant number of little tasks. Before we go any further, let's define jobs and tasks. A job consists of 1 or more tasks. A serial job can process only 1 task at a time. It performs the tasks in serial. A parallel job can process multiple tasks at a time. It performs tasks in parallel. A processing element is the smallest computing device capable of executing that task. A serial job can only make use of 1 processing element, and a parallel job can make use of multiple processing elements. In the past, a CPU was the processing element for a computer. CPU stands for Central Processing Unit, and CPUs were commonly referred to as processors. Later, multiple CPUs were incorporated into a node. Now, individual CPUs have multiple cores, and each of those cores is a processing element. CPUs with multiple cores are called processors. So what we have now is that a node contains 1 or more processors, and each processor has multiple cores. I want to point out that you don't need to be on the HPC cluster to use multiple cores. In fact, you are probably using multiple cores right now. I'm going to open up a browser and type cheapest laptop. Let's see what we can find. $74. What can we get for $74? It says dual core. This cheapest laptop has 2 cores. If we look into something a bit more pricey, like here's a computer, it has multiple cores. This one can be configured with 8 or 16 or 28 cores. Notice that when you buy one of these, you can also specify how much memory you want. You can specify a bunch of other things as well. Here I am logged into Henry2, and I'm going to look at the different types of nodes available. LS host shows the list of hosts, and host is another name for nodes. LS host shows the name of the node, the processor model, the number of cores on the node, and the maximum memory on the node. If we count how many lines were in that output, it shows that there are 980 nodes. We can parse through the output to list the nodes with GPUs. If we count the lines, there are currently 32 nodes with attached GPUs. There are many nodes that have the same model of processor. There are 4 nodes that have E52690, but there are 74 nodes that have this type of processor. Usually if 2 nodes have the same type of processor, they also have the same amount of memory, but that is not always the case. For example, this type of processor might have over 500 gigabytes, or it can have about 130 gigabytes. There are other commands you can use to find out more about the nodes on the cluster. You can check OS and kernel information with uname. You can check the version of Linux by looking in the CentOS release file. Type lscpu to find information about the node you are on. This node has 2 processors. Each of the processors have 8 cores, and that means there's 16 cores total on the node. You can see similar information by looking at the CPU input file. lscpu and CPU info don't have the memory information, so for that you can look at meminfo. The command to look at GPU info is NVIDIA SMI, but there are no GPUs on the login node. Let's do an interactive login to a GPU node. B sub minus IS is for interactive session. We're going to ask for 1 core, 5 minutes of time, and we have to specify the GPU queue for a GPU node. This next part has to be added to make sure the GPU is engaged, and TCSH opens a shell. Our job was submitted, we're waiting for a node, and here we are. Type NVIDIA SMI, and here's the information for the GPU. To leave the interactive session, type exit. In our documentation for Henry2, we refer to a node having multiple processors, each having multiple cores. The software definitions can be confusing too and might vary depending on who you talk to. We are going over these definitions because these are the terms used in all of the Henry2 documentation. A job consists of everything you write in a script and submit to LSF. When you run a job, you are doing tasks. You could do one or several tasks. The tasks can be related, but they don't have to be. If the work to be done by a task can be broken up into smaller pieces, those pieces are called threads. Tasks are sometimes called processes, and these terms can be used interchangeably. At the end of the day, the thing we want you to understand is how to request resources for your job. You have to request the proper resources to run your job, and that means you have to specify 1 core for each thing that you're doing. If your job is only doing one thing, request a single core. If your job is broken into simultaneous tasks, then request 1 core per task. And if those tasks can be further broken down into threads, then request 1 core per thread. Here's a diagram of a single node. The node has multiple cores, it has memory that is shared by all the cores, and it has a small amount of disk space. There are almost 1,000 nodes on the cluster. The nodes communicate with each other through a network. You submit a job with LSF, and if the job is a parallel job, it can be broken up into tasks or threads. You need to reserve 1 core for each task or thread. The network is the hardware that allows the 2 nodes to communicate, but the software that allows this communication is called MPI, or Message Passing Interface. If you or whoever wrote your application did not program the code to use MPI, your code cannot communicate over the network. Without MPI, the cores on one node cannot access the memory of another node. That means that all of the tasks must be confined to one node, where they all have access to the same memory. They share the memory. Parallel jobs that can only make use of one node are called shared memory jobs. If your code was written with MPI, the task can be distributed across multiple nodes because the memory used by the application can be distributed across nodes. Parallel jobs that can use multiple nodes are called distributed memory jobs. Now that we've covered all those definitions, it's time to finally run some parallel jobs. First, we'll review the sample batch script used in the previous tutorial. Then we'll discuss the modifications to the batch script that will allow you to submit basic shared or distributed memory jobs. This was the sample batch script used in the previous tutorial, and it contains everything you need to run a simple job. To run the examples in this tutorial, we're only going to add 2 more items to this list. The first optional argument to this list is b sub minus x, which specifies exclusive use of the node. The second optional argument is the b sub minus r span specifier, and that instructs LSF how to distribute the requested cores over the nodes. Let's go over the first optional specifier, b sub minus x. When should you use minus x? There is no hard and fast rule, so please just keep the following in mind. The resources are shared, and unless you specify otherwise, you could be sharing a node with others. Remember from watching the video on the acceptable use policy that the AUP means play nice with others. Do not oversubscribe a node by using a disproportionate amount of cores, memory, or disk compared to what you request in your batch script. On the other hand, you don't want to undersubscribe a node. Requesting more resources than necessary is not an efficient use of resources, and it unnecessarily increases queue weights for all users. The next optional specifier is b sub minus r span. The span specifier tells LSF how to arrange the cores over the nodes. The options are to specify that all the cores must be on a single node with hosts equal 1. The next option is that you can specify how many cores per node with p-tile. If you don't care how your tasks are arranged and the arrangement does not affect the performance of your code, you should go ahead and leave this out. To review, for a serial job, request 1 core. If your code is memory intensive, request exclusive use of the node. For a shared memory job, request the number of cores that will be used by the application and make sure all of those cores are confined to one node. Let's go back to the requesting cores part. If you wrote the application that you are running, then you probably know how many cores will be used, but what if you didn't write it? What if you downloaded it from Git or installed it with Conda and you've never used it before? The short answer is you need to read the documentation, but in general, an application will use a default number of threads, and the default might be 1, it might be some other fixed number like 4 or 8, or it might be all detectable cores on the machine. When looking at documentation for shared memory jobs, the parallel parts are almost always described as threads. If your application automatically spawns threads according to how many cores are on the node, then request the minimum number of desired cores and request exclusive use of the node. In this next exercise on running a shared memory job, you will be running an application that you didn't write yourself. The code is a version of Hello World. Each thread of the program says hello and reports the name of the node it is running on. The documentation states that the code is shared memory and will spawn threads equal to that specified in the environment variable OMP numthreads. To run the application, first copy it to your Scratch directory. Take a look at the included sample batch script and then submit the job. Try changing the number of threads used and rerun. Confirm the threading behavior using an interactive login. Make sure you are on a compute node before running anything. Use htop and top to help you look at what the code is doing. Here I am on Henry2. I'm in my Scratch directory in the guide folder that I created in previous exercises. Copy the parallel examples directory to this location. CD into the directory. Look at the script submit_shared.csh. It requests 8 cores, exclusive use, and specifies that all of the cores should be placed on one node. OMP numThreads is the environment variable that controls the threading behavior, and we have set it to 4. Let's go ahead and submit the job. The job does do some calculations, and it takes between 30 and 60 seconds to run. I'm going to clear the screen. Now our job is done. The error file from LSF is empty, and here is the output. The output is what we expected. It says hello from the thread number from the host, and all of the hosts are the same since we requested host equal 1. The application only used 4 cores, but we requested 8. If we hit space to go down and look at resource usage summary, we can see that the average memory used was 2.32 megabytes, and that is not very much. We did not need to use -x because of memory for this application. So let's modify the submit script and try again. I'm going to leave the number of cores requested to 8, but I'm going to use more cores. So I'm going to change OMP numThreads to 8. I'm going to comment out the -x, and I'm going to save it. I'll resubmit the job. The job is running, and now it's complete. Let's check the output again. I'll look at the latest LSF output. This time it used all 8 cores that we requested. It looks like we know what the code is doing from these initial tests, but let's confirm it with an interactive session. -sub -is request 1 core and -x. So we might use more than 1 core. That's why we'll use -x. You don't need the span when you're only requesting 1 core, but I'm going to put it in case you want to resubmit this with more than 1 core. You need to make sure all the cores are on the node. And when you use the -r with the span, when you use it in a command line like this, you need to put the quotes in there. Let's ask for 10 minutes and open a shell. Now we're on a compute node. Let's confirm by echo hostname. Let's do ls CPU. And that shows that the node that we're on has 2 processors. Each processor has 4 cores, so there are 8 cores on the node that we requested. To run the code, first we need to set the environment variable OMP numThreads, and we'll set it to 4. We're going to run the code and put it in the background. The standard out comes right to the screen, even though we put it in the background. So hit enter, then type htop. Htop shows that I am running 4 instances of the program hello_shared. So it looks like I am fully utilizing 4 cores on this node. We're going to do that one more time, and I'll show you top. So let's run it, put it in the background, and you notice htop moved. It was dynamic. If you want a time slice of what's going on, top -n1 for 1 time, and you have to add the -H to get all the threads, and there we go. Everything looks good. Let's exit the interactive session. When running a distributed memory job, request n according to the number of MPI tasks or processes. MPI jobs need to set the MPI environment and they need to use MPI run. That means you should be loading a module that has MPI and you need to add MPI run before calling the application. Note that with LSF, the value of n is passed to MPI run. Do not use an argument to MPI run unless there is a reason that it should be different from n. You also may want to specify the span, which means specifying the number of tasks to put on each node. There are two reasons why you might want to specify ptile, and in both cases you should also include -x. The first reason to limit the number of MPI tasks per node is because each task takes a lot of memory. If the reason you are using ptile is because you are dealing with memory limitations, you don't want other jobs competing for the memory as well. The second reason could be that you are running a hybrid code where MPI tasks may spawn threads. If the MPI tasks spawn threads, you need to use -x so that LSF does not assign additional jobs to those nodes. In this next exercise, you will be running a distributed memory job. The code is the same hello world that you ran in the previous exercise, except that it has been parallelized with MPI. Each thread of the program says hello and reports both the name of the node it is running on and which MPI task it was spawned from. Using the same directory as the shared memory example, open the sample LSF script and look at the parameters. Submit the job and look at the LSF monitoring and LSF output. Change the parameters and run again. Finally, remove MPI run from the script and see what happens. Here I am on Henry2. I am still in the parallel directory, and I'm going to look at submit_mpi.csh. We're asking for 6 MPI tasks. There should only be 2 tasks per node, so there's going to be 3 nodes used. We're asking for exclusive use of the node because this code is going to spawn 4 threads for every task. That means for every one of these tasks, 4 threads will be spawned. That means there'll be 24 threads running simultaneously. We have to load an MPI module and we have to use MPI run in front of the executable. Let's run it. While the code is running, let's do bjobs -L. That's for long form. It gives more information. I want to look at this. This says that it reserved 6 cores, and there are 3 nodes. 1, 2, 3. 3 nodes with 2 cores assigned to each node. Let's look at the output. The error file is empty. Let's look at the output file. And here we have lots of hellos. There should be 3 nodes that were used. So let's see, N2, D2, 1, 8, and 6. And those are the only nodes shown. So it did correctly reserve 3 nodes. There should be 6 MPI tasks. So here we go, 1 through 6. There are 6 tasks. Each task should have spawned 4 threads. So here we go, 1 through 4. So it looks like it worked. Let's modify the submission script and try again. Nano submit_mpi.csh and 6 tasks. Let's change it to 8. And ptile equals 2. Let's change it to 1. Okay, if we're asking for 8 and we only put 1 here, that means we need 8 nodes. And this is sort of a waste of nodes, but let's just make it bigger, 8. So now we should reserve 8 nodes, and there's going to be 1 MPI task on each node, but they should spawn 8 threads each. So we should be running 64 tasks. I specified ptile equals 1 and 8 tasks per node, but what if I get a node with 32 cores? Then I'm being very wasteful. So let's go back to the HPC website and see if we can specify an 8-core node so we're not wasting resources. Go to the HPC website, click Documentation, Running Jobs. Go to the generic template for batch scripts, scroll down, and hit Select Resource Type. We want to select a resource type of a node with 8 cores. So let's go to LSF Resources for more information on this. Scroll down to Resource by Processor Type, and each node has 2 of the same model processors, but the resource type description is in terms of processors. So DC is for dual core, and that means there's 2 cores on the processor, 4 cores on the node. So what we want is quad core because we want to make sure that there are 8 cores on the node. So QC is for quad core. I am going to copy this specification and let's put it in our script. Doesn't matter where you put it. I'm going to go ahead and put it here. It needs to start with bsub. All the commands for LSF start with bsub, and I'm going to paste it. Capital R for resource. Go over and change the resource type to quad core processor. Quad core processor means there's 4 cores on the processor, 8 cores on the node. We're requesting 8 MPI tasks, 1 task per node, 8 threads per task. There should be 64 total threads. Let's save it and run it. Let's look at the output. I'm going to use less. The error file is empty, so that's good. I'm going to copy and paste. There are 8 MPI tasks. There are 8 MPI threads. If we go and count the lines, there should be 8 different nodes used, and there should be 64 separate threads that were used. Let's go back to the instructions. It says edit the submit script to remove MPI run and resubmit. What happens? So we'll open the submission script again. And this time we're going to pretend that we forgot to do the MPI run. I'm just going to get rid of it. And run it. There is no error. This is the output. We look at the file and let's see. We asked for 8 MPI tasks, but it only gave us 1. There were 8 threads spawned, but there's some bug in the code because it thinks it's saying hello from thread 5. All of these threads were on the same node, but we still reserved 8 nodes. So we were only using 1 node out of the 8 that we asked for. So that was a lot. So go ahead and pause the video and try this exercise a couple more times. Change the parameters, see what you get, and go back to Henry2 and look at the resource types. Congratulations on finishing the Basic HPC Workshop. For more information, always check back with our website. Check the documentation on running jobs, and click Support, Links for Learning. Scroll down to the recommended resources on learning more about high-performance computing. To be notified of new videos, please subscribe to the OIT HPC YouTube channel. To find more information about a specific video, click on the video and scroll down to show more.